Hello, everybody. We start with a question. Awesome, Brooke. Thank you so much. You know what? Brooke just noticed that I have been neglecting to say what chapters of my book correspond to the uh, lectures here and weeks, and that's absolutely true. So there's a rough, you will see some connections on the weekly exercises. So the weekly exercise, okay. The weekly exercises uh, actually ask you to do some exercises from a specific chapter. By the way, let me get my book. All right, so here's the book. Um, all right, so the weekly exercises, in each chapter has a list of exercises at the end. For example, let me go to chapter 2. So chapter 2 has, which we are not going to cover here, I think, but it has a list on page 22nd. It has this one. Oh man, this sucks. The light sucks. It's not the picture. It's this on this side. There's a list of exercises. Okay. And so the weekly exercises, I typically say, do exercise 2.1 or from chapter 2 or whatever, do exercise 10.1, things like that. And so at that point, when you do the exercise, you should read that particular chapter, okay? So I use the lectures as a context, a much broader context to the book. So the book is very much focused on, here's how the style looks like. Okay, here's an example of the style. Here's the context in which that style emerged. When was it first, kind of, who were the people who were doing that? What context did it emerge? And then there's a list of exercises at the end. The lectures that I do here are much broader. So I talk a lot more about lots of things that kind of didn't fit the mold of the book. As you will see, for example, right now, this lecture, I'm going to talk about Turing machines. And I don't talk about Turing machines in here. Well, actually, you know what, now that I thought about it, maybe I should put the Turing machine exercise here. It would be hard to do. 10 frequency in Turing machine would be a kind of an interesting challenge. Anyway, so there are things that I talk in the lectures that didn't make it to the book because it just didn't fit the mold of every chapter. So, but nevertheless, I will add here. Let me make a note that the chapters, add the chapters to the syllabus. Okay, so that you know where we are. Okay. All right, so let's talk about Turing machines and Turing, Alan Turing in particular. And I'm sure that almost all of you, if not all of you, have heard about Turing. He is a pretty important guy in computer science. In fact, he's sort of, didn't quite invent, but is definitely the father of computer science, along with a few other people. Of course, you have all heard about the Turing Award. Yeah, it's like the Nobel Prize of computer science. And the reason is that this guy, I mean, he wasn't the only one, but he had an absolutely gigantic influence on the existence of computer science. And maybe you have seen that movie. What was it called? That movie that was around like 5 or 6 years ago. What was it called? Remind me. You know what I'm talking about? Alan Turing. Oh no, I lost my windows of Zoom.
It was the Imitation Game.
Imitation Game, good. Yes, I recommend everybody to go and see it. It's a really good movie. But basically, it's an edited and a movie version of Alan Turing's life. In particular, around the time of the end of the Second World War, as it unfolded, that turns out that Alan Turing had an absolutely, again, gigantic influence on the outcome of the Second World War too. But so he was a mathematician, but he was also, he was also an engineer, because he took part of the building of some of those machines that cracked the Enigma codes from the Germans. So, and you can see that in his paper. So before the Second World War, just about when the war was about to start, just a few years before, in the mid 1930s, he wrote a paper that would be super influential, and I have that linked from the course's website, and I highly recommend that you read it. It's really interesting. Now, bear in mind, it's a mathematical paper. Okay, it was published in a mathematical journal, so it's super abstract. It has a little bit of Greek letters, not a lot, but a little bit, and so it may be a little hard to read rather than just a textbook describing the Turing machine. But that is basically the source. That's the source of the Turing machine material. So if you are curious about the history, about if you're curious about computer science, I highly recommend that you read that book, read that paper. And basically, that was the paper that presented his idea for a universal computing machine. Let me give you a little bit of context. What exactly does that? Now, in order to give you some context for that paper, I have to go even a few years back. Starting sometime in the late 19th century, there was a branch of mathematics, and especially in the early 20th century, there was a bunch of mathematics that started emerging, that started questioning even the foundations of mathematics. Okay, that started questioning about what exactly are we computing? What exactly what's calculus, right? What is a calculus? What exactly are we calculating? What kinds of calculus can we have? Can we have alternative calculus, right? And so basically there was, but what kinds of functions can we compute? We know logarithms, we know integrals, we know polynomials, we know about a lot of functions, but what functions don't we know? Are there even functions that we don't know? Right? Are there functions? We have at the time were not called algorithms, but we have methods for calculating the values of functions. Given an input, we have methods to calculate what the output of a function is, and those were later on called algorithms, right? Those methods. But are there functions for which there are no algorithms, right? Are there functions out there? We can imagine that maybe there are functions out there that there are no algorithms for calculating those functions, and there are perfectly fine functions, except that we don't have methods to calculate, given input, what the output is. And so all of those really interesting, intellectual challenging questions were starting to percolate in certain circles of mathematics, basically questioning what was the nature of mathematics, what was the nature of calculus, and what exactly were we calculating, and whether we could calculate everything that we could imagine, or whether or not, or whether there were limits for what we could calculate. Basically, the nature of functions. And so that emerged. Very much later on emerged with the conjectures about whether the functions that we can calculate are the P functions, and the things that we cannot calculate are the NP things, and so whether one thing is equal to the other. Lots of the incompleteness theorem that came sometime early in the 20th century, all that stuff. So that comes from there. And so at some point in the 30s, okay, Alan Turing, in 1936, published this paper about the functions that can be calculated. Okay, so for the functions that can be calculated, he showed, okay, how to engineer a machine. And basically, his paper is a mathematical paper, but it's also an engineering paper. There is the core of a machine in that paper. That's the beauty of that paper. There's a machine in there that is describing in mathematical terms. It's just beautiful. But basically, he showed that even that machine can basically calculate everything that can be calculated. Now, the functions that we don't know how to calculate them, forget it, we cannot calculate them with this machine. But the ones that we can calculate, any algorithm basically, can be done with this machine, and he proved that. That's the mathematical part of his paper is the proof of how that is true, or the conjecture, or close to be proof that might be true. And so that is sort of the absolutely fundamental result in 1936 by Alan Turing. And before I even continue to talk, today's lecture is about Turing and Turing machines, but let me just give you a little preview what's ahead that I'm going to talk about next week, or the other, I don't know, one of these lectures. I'm going to talk about another paper and another foundational result that was published in exactly the same year. It's quite coincidental. 1936 was an amazing year for computer science. And that was another paper by another mathematician called Church, Alonzo Church, okay? And he too published a paper that had a calculus for calculating anything that could be computed. Okay, completely different from the Turing machine. That's the lambda calculus. Right, I'm going to talk about the lambda calculus a few lectures ahead, and that's another super interesting thing. I mean, this is really foundational material in computer science. Every computer scientist should know about these things, okay? The Turing machine and lambda calculus. And they came 2 months apart. That's a crazy thing. 2 months apart. And they basically proved the same thing in completely different ways. They proved that they had 2 different mechanisms for computing everything that could be computed. Okay, they were universal in nature, but in completely different ways. Okay, so today is about, and by the way, the way that computer science kind of unfolded is that because Turing, I think this is my interpretation. Now I'm going to move into my interpretation of history. I think because Alan Turing was not just a mathematician, but also an engineer, and he had very much a very strong influence on the engineering of the computers themselves. I think that, the way that our field evolved towards the Turing machine kind of model. Okay, and then we see that going into the first programming languages, things like that. So with imperative languages come from the Turing machine, as you will see. So it had an enormous influence on the sort of the early history of computers and programming languages and things like that. Alonzo Church, on the other hand, the lambda calculus is the foundation for what's called functional programming, functional programming. And for a while, functional programming was a complete niche. Okay, it was the niche of mathematics. It was still a branch of mathematics for the longest time. And only recently it started having some practical, implications and some interesting software engineering consequences from functional programming. But I think, it had not, Alan Turing had this influence on the actual engineering of computers, maybe things would have gone the other way around. It's kind of hard to tell. But so Alan Turing, let me talk about him. His computer model, which you will see, if you read the paper, you will see it's there, described there in very mathematical terms, but nevertheless it's there, is basically an inspiration for the actual physical computers that came not that long after, actually, just a decade after, and it basically started developing during the Second World War. So he was instrumental for cracking the Enigma machine from the Nazis. For those of you who don't know, the Nazis the Germans had an advantage during the Second World War in that they had a killer cryptographic system. So they used to send messages over radio waves, but they were encrypted. So if you want to send a text message, they used some cryptographic keys switch the letter A to whatever. But those keys were really, really hard to crack. In fact, they remained uncracked until the very end of the war. And so the British set up a lab, an institution, Benchley Park in England, for the sole purpose of trying to crack the keys of the cryptographic system that the Germans were using. Okay, and so that's where Alan Turing was working. He was working there to crack the code, and cracking code means basically trying and erring many times, and as fast as possible, right? So if you can try many times and it's very fast, you eventually crack it. Because, I mean, in retrospect, the keys that the Germans were using were not very sophisticated, but they were sophisticated at the time for humans to crack, right? For humans could not crack it. So it had to be faster than humans. So faster than humans means having some sort of a automated machine who would do whatever the humans were doing to crack the code. Basically try and fail until you actually succeed. So he also invented what's called the Turing test. That was later after the Second World War, which was, to challenge the community to come up with a machine which would be so smart to answering questions that you would not know if it's a machine or a person. It would be indistinguishable from a person. So that's called the Turing test. And I have a feeling that we passed that line already. There are some automated systems out there that sometimes you cannot tell whether it's a person or a bot somewhere. And of course, the legacy here is the Turing Award that is given to computer scientists, or one or more every year. So Turing was inspired to build a machine that could think like people. That's basically where all of these earlier computer scientists, they were trying to pursue. They were actually indistinguishable from cognitive sciences in many ways. They were much closer to cognitive science than we are now as computer scientists. So they were really trying to kind of do a machine, and guided by the naive belief that it would be relatively easy to mimic what the brain does. But basically, this idea that would be an electronic brain that would do the same thing that humans could do. His model, Turing's model, was also very, very simple. The Turing machine it's like a kid's toy. Okay, it's not sophisticated at all. You can do it. You can do it with stuff that you have lying around. It's a very simple machine. Basically, imagine a super organized, obsessive compulsive human computer. The computer wants to avoid mistakes, so everything is written down, completely specified, and the computer follows a set of rules. And the rules are such that at any given time, only one rule is active, so there's no ambiguity ever. And each rule activates another rule depending on what the letter number is. So it was hard to believe that you could actually do all the functions, calculate the values of all the functions in the world by something as simple as that. But that's basically what Turing proved. And then a few years later, it was proven that whatever Turing was doing was equivalent to whatever Church also did with the Lambda calculus. So let me talk about the Turing machine. And I wish, you know what? I wish I had a picture of the Turing machine. Let's see if I can find a picture of a Turing machine. That really sucks. I would have imagined that would be better pictures of a Turing machine. So something like this. Something like this, not bad. Can I have a zoom, please? Can you see this? Yeah?
Yes.
Okay. So this is what a Turing machine looks like. This is what Turing was envisioning in his brain in the middle of the 1930s. So it consists of a tape that can go left and right. You can go in both directions. It has a reader, okay, so a head that reads. So the tape is divided into slots, all right? So every slot has some sort of a number or a digit of some sort. And to simplify things, assume that there's only two kinds of digits. There's a 0 and there's a 1. And then there's the absence of a digit that is also, that there's nothing there. So 0 or a 1 and there's nothing there. So the tape has these slots at fixed sizes, like a measuring tape, right? And so it can go left and right. And then you have a reader, that's this machinery here that's on top in the middle, right? And the reader is placed on top of the tape and is capable of both reading what's there, what digit is there, and also of changing what's there. Okay, so it's actually not just a reader, it's a reader-writer, okay? So it can both see what's in there and it can change it too, okay? And so this is it. This is the toy that Turing envisioned. And basically what he's saying, the core of his work is that a device as simple as that can compute any function that can be computed. Okay, any mathematical function that can be computed. Every logarithm that you can think of, polynomials, whatever, everything that can be computed by a machine like this. Okay, it's mind-boggling because this is such a simple machine, right? It's completely crazy that it's not obvious at all how you can compute everything with something as simple that looks like a kid's toy, right? So let me explain here. Yeah. Let me go back to where I was over here. Let me show you how this can compute I'm going to show you that this is true just for one function, okay? A very, very simple function. That's the successor function. Successor function is given a number, it returns the next number, the next integer. Okay, we're given an integer, it returns next integer. If you give it 3, it returns 4. If you give it 126, it returns 127. Okay, that's all it does. So I'm just going to show you how you set up the machine, the data, basically how you set up the data and how you set up the rules, the program. And I'm going to talk a little bit more about the program so that you can implement the successor function. Okay, so here's how it goes. Here, I'm just going to tell you the rules, and I'm not going to tell you where these rules come from. I'm just going to tell you where the rules are. So here are the rules. The program, okay, this is the program. Basically, these rules are the program. If the reader reads a 1, if it's a 1, then write a 0 and go to the right. And then repeat, okay? If it's a 0, then write a 1 and stop, okay? And then if it's nothing, that's what this little thing, if it's not there, it's nothing there, then write a 1 and stop. All right, so these are the 3 rules, the program that controls the machine's movements, the machine's actions, so that it implements the successor function. Now, let's see how this can work, because in order for this to work, we have to think about the data and how to lay out the data very carefully. So this program works only if we lay out the data in what's called reverse binary. Okay, if you want to do it in straight binary, then you probably have to do it the other way around. Instead of going right, to go left, or left or right, something like that. I leave that as an exercise. How would you do this with a straight binary instead of reverse binary? So let's see how we can do this in a tape that can. So you start the tape. So what's on the tape when you start? When the tape starts, it's supposed to have the input, okay, the x. So we're calculating functions, right? So functions receive input, and at the end they have output. When the machine stops, there's the output. That's what it means to compute a function. So when we start the machine, we have to already have the input on the tape. Okay, so we're going to put reverse binary 47 on the tape, which is this thing. Okay, so if you just write it down, try to write 47 in binary and then flip it around. Okay, so this is the most significant bit, the right one, and the left one is the least significant bit. So it's the other way around. Okay, right. So this is 47. So here we go. How do we execute this program? If we start from the beginning, okay, from here, if it's a 1, write a 0, go right and repeat. So in this case, yes, it is a 1. So we're going to overwrite it with a 0, and we go to the right. Okay? Oops, here. So we wrote a 0, and we went to the right. So now we do the program again. It's a 1, we write a 0, we go to the right. Okay, same thing. It's a 1, we write a 0, we go to the right. Same thing. It's a 1, we write a 0, we go to the right. Now it's not a 1, so we go to the second rule. It's a 0, write a 1, and stop. Okay. And lo and behold, if you look carefully, we now have 48 in reverse binary. Yeah. Magic. So I encourage you to do it with other inputs if you want. But basically, what I'm saying is the following. These things, if with 1, write 0, go right, repeat. If with 0, those rules is the program that drives this particular function. Okay, it's this particular function. If you want to compute another function, you have to have other rules, right? This program is written for this particular function. And so this is the program, and we have this tape that is both has the input, and it's when the machine stops, it's going to have the output, right? Now, coming up with these rules with this program, that's the sauce, right? That's the secret sauce. If you want, for example, to calculate, oh, I don't know, whatever, x squared or something like that, okay? You're going to have to kind of spend some time thinking about how are you going to calculate x squared in this crazy machine that goes left and right and overrides things, right? And also you may want to do some, nice little tricks with respect to the representation of the input. Some representations are better for certain things. So maybe it's straight binary, or maybe it's reverse binary, or whatever, some floating, I don't know. So the representation of the input may also play a role in how easy this program is going to be. Easy or complicated program is going to be, right? But basically the sauce here is in kind of devising how to write these rules to drive the machine for doing what we want to do. That's not trivial, obviously. Can we also store what we did in the past? No. So that's an interesting thing, but in the Turing machine, you cannot express that. So the Turing machine cannot remember what was done. Now, at least not like this. So you may be able to remember by these primitive things, okay? So you may be able to code up some storage, some memory, by having some maybe special symbols that tell you go to, I don't know, three times ahead or something like that. So it may be possible to have these programs, these higher level programs that you code up in the very basic, simple Turing machine, the only actions that you can do is go left, go right, read and write. That's all. But then, based on these very simple, these things, these very simple actions, then you may be able to have sort of compound actions based on these things that allow you to do more powerful things, right? And you can imagine, now that we have a successor function, now we could have the successor function be, a little module for something that is more complicated too. But so the Turing machine does not remember. And the Turing machine, the other thing about the Turing machine, at least as Turing devised it, and related to memory, by the way, related to state, the Turing machine is thought for functions. Okay? We come back to functional programming. Functions don't have memory, right? Functions is something that you give it an input and you get an output, and that is completely independent of any other inputs and outputs that you got before. In mathematical functions, there is no memory, right? And I don't know how many of you here are studying neural networks and machine learning and stuff like that. There's an interesting thing in there, that neural networks are also very much kind of functional. And people are trying to kind of build memory systems on top of something that is basically stateless. And so the Turing machine is also a stateless machine. It does not remember anything. Now, this is not to say that the computers that were built based on inspired by the Turing machine were very much stateful, and the issue of memory came very early on, knocking on people's doors. And I can talk a little bit more about that. But the Turing machine is basically stateless because it was thought for and designed to calculate the values of functions. And functions, you don't remember anything about what happened before. All right. So that was that. You can plug in more numbers in reverse binary. You will see that these rules will produce the right results. So this is what happens if you plug in 127. You end up with 128. Basically, just this is 0, 0, 1. So on the last one, it's a 1, write a 0, go right. And now there's nothing. You write a 1 and you stop. Okay, this is when you add the most significant bit at the end. Right? So this is kind of cool. The slides I have this is the end of my slide deck, but I have more things to say about Turing machines and Turing in general. So the first one is that what happened next was that Turing was asked to join Benchley Lab, or whatever it's called, Benchley Park, to crack the Enigma machine. And they basically started building computers that were sort of like this, based on this model. Basically, there were these tapes that you put the input, and the tapes could rotate, go left and right. Basically, you have the readers and the writers, but there was more sophistication going on in here. There was sophistication in terms of how do you write these rules, the rules of the program, right? That typically were in the beginning were very much kind of mechanical knobs, electromechanical knobs. So there was at the same time that this was going on in England, there was also another effort here in the United States, led by von Neumann, that was also looking into building, powerful computers that went beyond the Second World War. In particular, they were looking for business applications and things like that. But so von Neumann was very much aware of Turing's paper and Turing's ideas for a universal machine. He did something that was more engineering. It's a lot of engineering, not just mathematics. And so he did. In particular, he addressed the issue of memory, right, and state. And one thing that he did with the computers that he was basically designing was this idea of the following thing. So here's how computers were programmed in the beginning when people started having computers. Imagine that you have the computer, the way that you wrote these rules, as I said, was turning knobs for particular values, right? So every time that you wanted to change the program, you would have to change the knobs for a certain particular value. So that became old very fast because you wanted to repeat the program and you had to turn the knobs all around. So immediately one of the things that they needed to solve is how do you store a program? Right? How do you represent a program? How do you even represent a program that basically in the computer it looked like values of electromechanical valves, and how do you store it externally, right? And then once you store it externally, when you want to load it back, okay, you load it back so that automatically those knobs go to the right places. Okay, that was the beginning. That was von Neumann's contribution to computer engineering in particular. That he came out with the design of a machine that was capable of both representing the program externally to the machine and then loading that program to memory, right? So basically, the program was stored externally in maybe it was on a tape. At some point, it was the technology that was used to start the program was these punching cards. Maybe some of you have seen these punching cards. Maybe not. Let me try to find a picture of a punching card. These things here. All right. Okay, this is very old technology. In fact, this is even older than you think. Okay, this was not invented for computers. This was invented for looms. Like in the 19th century, the Industrial Revolution, doing fabrics and patterns in fabrics. The way that they represented those patterns was pretty much using these punch cards, right? So each pattern had a different kind of pattern on the punch card, and so they loaded up. They loaded the pattern by reading these holes on the punch cards, and then having the loom do that automatically. Right? So this technology came from the 19th century, from the looms, and then it was used by computers. Right. So basically, as you can see, given that at the time, the program, so these rules are basically values of knobs, right? What these holes represented was these values of those knobs, right? And so you were able to store the program externally on paper and then have a reader of these holes that would basically load it up, meaning that turning the knobs automatically to those kinds of values, right? So that was the beginning of this part of the memory, in a way, that you load up, that you store the program externally and then you load it up into quote memory, and then you have a truly universal machine that you don't need a human to actually go turn the knobs every time that you want to run a program. You can start the program externally. So that's quite an interesting thing that happened there, and then after that, once people started realizing, oh, you know what, I can have a piece of memory in my machine that I can look up, right? So I can have, for example, I can compute a function for a given input, and then I can store the value of that function and the calculation. I can store it somewhere, right? And then I can compute another function and I can do something else with the value that I previously computed. Right? So this idea of having a memory, an external memory that is external to the computation itself, right? And that is the state, right? That was very natural. That was came from von Neumann architecture, and basically the idea that you have a memory that you can look up. You can store stuff and you can look up. You can look it up. that came from basically thinking of computers as machines that can do a bunch of actions, and whatever is convenient for us for what we want to do, we can do that. All right, so that's one thing that I wanted to talk about Turing machine, and what happened next was the von Neumann architecture. And then, but the other thing that I also want to kind of point out in terms of programming languages, these rules that you're seeing here on this slide, if read 1, write 0, go right, repeat. This is the program. This is the program. What is the program? The program is basically the specification of a bunch of actions that the machine can do. Right? It's very much a specification for how we want to drive the machine. Go left, go right, read, write, stuff like that. It's very much a kind of an imperative style. Right? We have a machine. The machine provides us with a set of actions, of things that the machine can do. And so what is the program? The program is us specifying exactly what the machine should do. Okay? That is what the program is. You're going to see in a couple of lectures when I talk about lambda calculus that the program is something completely different, has no machine, there's no actions. There's something a lot more abstract, a lot more esoteric. And it's quite interesting that two approaches that are so diametrically opposed are capable of doing exactly the same things. It's really, really interesting. But so, what we have here is basically the beginnings of imperative programming. Imperative style. What is imperative style? It's basically this idea that we have at our disposal a set of actions, okay? And we are the ones who have to specify what the actions are in order to have some results at the end. Okay, that's basically what imperative programming is. So go left, go right, some glorified version of going left and going right and reading and writing what's there. so that's kind of interesting thing. So the way that programming and programming languages evolved, this is the beginning. This kind of driving instructions were the beginning of programs and programming languages, and they set pretty much the tone to imperative programming. Basically, you have a machine, and your role as a programmer is to drive it, to write the specification that drives that machine. And all of the mapping between the high level function, because at the end, essentially these programs were doing calculations. That's what they were doing in the beginning. But the mapping from those mathematical calculations to the low level actions of driving the machine, that was still pretty much an art, right? And it had to be done by people, by programmers. And this was basically the algorithms, right? Those were the algorithms, the things that were able of driving a machine so that at the end, we would get the function that we wanted to implement. All right, so this is where algorithms come from. It's very different from functional programming when I talk about functional programming, completely different. All right, so this is a little bit of history. So the other piece of more personal history of Turing is that the poor guy turned out, he was gay, and in a time when being gay was a crime, actually, literally a crime. So he had a horrible end of the life. I mean, this guy made so many things. He did so much. He basically helped end the Second World War. He single-handed created computer science. He helped create the basic engineering and architecture of computers. And then he was mistreated like an animal. It was really, really horrible the way that they treated him. They forced him to take these chemicals for castrating, for basically chemical castration. And I mean, the guy ended up killing himself because he just couldn't take it anymore. And what a shame, because he was on the way to do lots of more amazing things. He was involved in lots of other ideas. He was a very creative guy. He was doing biology, sort of computational biology. He was sort of the father of computational biology too. He was a really amazing person, and he had such a horrible end of the life after doing so much. So that's a sad part. But anyway, I hope that my little lecture here encourages you to go read his paper, which is an actually beautiful piece of history in computer science. Do you have any questions about Turing or Turing machine?
Professor, I have a question.
Yeah.
Are algorithms themselves functional or imperative? I'm kind of confused on that.
I'm sorry?
Can you call an algorithm imperative, or can you call it functional?
An algorithm is very much an imperative thing.
So are there functional algorithms as well?
No. By definition, I'll talk a little bit more about this when I talk about functional programming. But the beauty of functional programming is that it tends to describe functions. Basically, it doesn't, in principle, it doesn't get away from the mathematical realm. Okay, and the mathematical realm is more important with the what than with the how. Okay, so the mathematical realm is worried about what do you want to do, right? You want to do a polynomial or whatever, x squared or x squared plus 1. That's what you want to do. It's not worried about how you're going to do it. What is the process by which you are going to transform an input, a specific input, into an output? And it's particularly the process of driving a specific machine. Okay, and so a lot of what we learn in algorithms is very much some sort of a, even if you use a higher level pseudocode. The idea of using sort of loops, for example, okay, conditionals or things like that, those are things that come from trying to control how things are going to unfold. And once we go into controlling how things are going to unfold, then you are dangerously close to imperative programming.
Okay.
All right. I'll talk a little bit about that, and I'll functional programming, the spirit and the principles of functional programming is actually pretty interesting. There's the mathematical underpinnings of functional programming are actually quite interesting, and I'll talk, when I go there, I'll talk a little bit more. But basically, what you need to know about it right now is that if we feel that we need to say, if this, then that, and if that, then whatever, and I'll loop 10 times, and stuff like that. That is basically we are trying to inject our own ideas about how to do things, right? And the how is imperative. The what is functional.